Good morning and welcome to Mission Control Houston and Space Station Live. We're here in the International Space Station Flight Control Room where the International Space Station Flight Control team is watching over all of the crew's activities in space. Flight Director Tony Sakachi is leading them today, and astronaut Megan MacArthur is in the Capcom seat. The Expedition 36 crew is now more than halfway through their day, which began at 1 a.m. Central Time. They are Russian Commander Pavel Vinogradov, U.S. Flight Engineers Chris Cassidy and Karen Nyberg, European Space Agency Flight Engineer Luke Parmitano, and Russian Flight Engineers Alexander Misurkin and Fyodor Yurchikhin. Cassidy, Vinogradov, and Misurkin launched into space on March 28th and docked a few hours later, so that they've now spent 125 days in space. Nyberg, Parmitano, and Yurchikhin followed in their footsteps on May 28th, so they've now spent 64 days in space and at the station. Together, the crew is currently orbiting 258 miles above the border of China, heading northeast towards the northernmost portion of this orbit around the Earth. Inside, Cassidy and Nyberg were back at the space station's robotic workstation today, getting ready for the arrival of the Japan Aerospace Exploration Agency's Kounotori H-2 transfer vehicle number 4. That vehicle is set to launch from the Tanegashima Space Center in Japan at 2:48 p.m. Central Time on Saturday, and then make its way to the space station on August 9th, where Nyberg and Cassidy will be waiting to capture it with the space station's robotic arm and bring it in for a berthing on the Harmony node. Today they're brushing up on their skills for that activity. Nyberg is also spending a good bit of her day getting ready for the InSpace 3 experiment. That's an experiment that looks at how magnetic fluids are influenced by magnetic fields in microgravity. It could help engineers here on the ground design structures such as bridges and buildings to better withstand earthquakes. View here of Nyberg working inside the microgravity science glove box where that experiment will be housed. Besides these science experiments, Cassidy and Parmitano are each doing some maintenance work on some of the science facilities at the space station. Parmitano is troubleshooting an issue with the handling mechanisms drawer for the European Space Agency's Biological Experiment Laboratory, which provides an on-orbit biology laboratory that lets scientists study the effects of microgravity and space radiation on uni- and multi-cell organisms such as bacteria, insects, seeds, and cells. And Cassidy is performing a checkout of the combustion chamber in the Japan Aerospace Exploration Agency's multi-purpose small payload rack. You can see him inside the Kibo laboratory where that equipment is housed in this video from earlier today. And on the Russian side of the space station, Commander Alexander Vinogradov is continuing his work to unload the Progress 52 resupply vehicle that arrived at the space station on Saturday. And his Russian crewmates are working on several different experiments, including one that looks at cultivating different types of cells in microgravity, and one that studies the creation of methods and equipment for producing aseptic conditions for conducting biotechnology experiments in space. That's what's going on in space today, and this is Mission Control Houston. A large portion of flight engineer Karen Nyberg's day has been devoted to getting the InSpace 3 experiment set up inside the station's microgravity science glove box so that they can start that experiment up soon. InSpace is actually an acronym for Investigating the Structure of Paramagnetic Aggregates from Colloidal Emulsions. And that experiment is intended to study the fundamental behavior of magnetic colloidal fluids under the influence of magnetic fields. You can see in this video from earlier today, Karen Nyberg working at the microgravity science glove box where that experiment is housed. Colloids are mixtures of one substance microscopically dispersed throughout another substance, and magnetic colloids form a rigid lattice that causes the suspension to stiffen when a magnetic field is applied to the fluid. The study of magnetic colloids on Earth is difficult because in gravity their paramagnetic particles sink while the magnetic field is applied, affecting the formation of the structures they would otherwise create. But observing the structures in microgravity can give us a better understanding of how magnetic surface and repulsion forces interact in magnetically responsive fields, and the lack of gravity on the space station helps scientists do just that. This knowledge will be useful for space applications because these fluids are used in electromechanical interfaces and devices in which the fluid is exposed to magnetic fields that can affect their operation. That includes devices such as tunable dampers and brakes, and in the future could include robotics, clutches, and a host of vibration-controlled systems as well. And the study also has benefits here on Earth. It could improve our ability to design things like bridges and buildings to better withstand earthquake forces. To get the InSpace experiment set up today, Nyberg needed to install the InSpace hardware and cables, as well as the bioassemblies and video cables, which you can see video of her doing here, and also configure the microgravity science glove box video system. Next big event on the space station's horizon is the launch of the fourth Kounotori H2 transfer vehicle from the Tanegashima Space Center in Japan on Saturday. That's scheduled to take place at 2:48 p.m. Central Time, and you'll be able to watch it here on NASA TV with coverage beginning at 2 p.m. The HTV-4 is going to be carrying to the station experiment samples and equipment, including Frost, the freezing refrigerator of Stirling cycle, which is able to maintain a negative 70 degrees Celsius temperature and stay cool even without power. And Icebox, ICE being an acronym for ISS Cryogenic Experiment Storage. The vehicle will also be carrying another eyeball experiment, which is a reentry data recorder that will relay information on the HTV's return to Earth and then burn up in the Earth's atmosphere when its stay in space is over. And there's also a number of supplies, food, water, and clothing for the crew aboard the station. The HTV-4 won't actually make it to the station until August 9th, when it's scheduled to be brought in for berthing to the station's Harmony node at 6:29 a.m. Although most of the other vehicles that visit the station dock automatically, the HTV is actually captured using the space station's robotic arm and driven by the crew to the Harmony node.
Please respond.
So the crew has been spending a good deal of time getting ready for that activity. You can see here some live video of Karen Nyberg working at the station's robotic workstation inside the Destiny Laboratory, along with Chris Cassidy. They've been spending a good deal of time brushing up on the robotics training to ensure that they'll be ready for the task when it comes. Although they, of course, trained for this activity before ever leaving Earth, they want to be sure that all the processes and setup is fresh in their mind so that they'll be able to safely bring the HTV in for the berthing to the Harmony node. You can see here a graphic representation of what the crew is training to do. The HTV here approaching the International Space Station and then moving in a bit closer to get within range of the station's robotic arm. On August 9th, again, Cassidy and Nyberg will be at the robotic workstation controlling the robotic arm as it grabs onto the HTV and then brings it in for its berthing to the Harmony node, as you can see here. Back again with live views here of Nyberg working at the robotic workstation, practicing for that activity that you just saw the graphic representation of. Again, she and Chris Cassidy will be the ones actually controlling the space station's robotic arm and bringing the vehicle in for its berthing. one of the activities that Luke Parmitano is going to be taking some time out of his duties for today is to contact via ham radio students with the Experimental Aircraft Association attending the Oshkosh AirVenture Air Show in Oshkosh, Wisconsin. The crew on board the space station is often able to talk with students that way through opportunities arranged by the Amateur Radio on the International Space Station program, or ARIS for short. You can find out more about that program at arrl.org. Again, that's arrl.org. And its goals include inspiring an interest in science, technology, engineering, and math, or as they're better known, STEM subjects, and also in STEM careers among young people. Also providing an educational opportunity for students, teachers, and the general public to learn about the space exploration, space technologies, and satellite communications. And then they also hope to provide an educational opportunity for students, teachers, and the general public to learn about wireless technology and radio sciences as well. And then it also gives an opportunity for amateur radio experimentation and evaluation of new technologies. Today's ham radio contact is taking place just before noon Central Time, and we hope to be able to record and play it for you during tomorrow's Space Station Live. Many of the science experiments and technology demonstrations that go on board the space station require little to no involvement from the crew, and one of those going on today is the SCAN experiment, or Space Communications and Navigation Testbed. This is a technology demonstration project that's been on the station for about a year now, and we have on the phone Sandy Johnson, the Deputy Principal Investigator for SCAN, to tell us a little bit about it. Hi, Sandy. Thanks for joining us.
Hello. Good morning. Yes, and what I want to talk about today is the SCAN testbed, which is a testbed that we have installed on an outside truss on the space station, so you can actually see it when you look at the space station, when you see pictures of the space station, which we think is pretty neat. Um, it was launched about a year ago from a launch vehicle in Japan and installed on the space station. And a couple weeks later, we turned everything on and made sure everything worked. And we've been operating it for a year now, and it's working perfectly.
So, sorry, what exactly is SCAN? What does it do?
Okay, what it is a test bed to test the next generation of radios. And radios is a term we use for like a wireless modem. So in your house you have a wireless modem, or your cell phone is a modem, a way of taking information that you have on your computer or on your phone and sending it through the air without wires to another system. And NASA typically had these radios were in hardware, so when you built them, you couldn't change them after you built them. So you know how with your radio or your cell phone you have new applications you like to add, or I like to add a lot of new applications to my cell phone, and that makes it do things that you didn't intend to do when they were first built. So for NASA, we couldn't do that. We had to, whatever we build it with is what it stayed with to do, and whoever it could operate with at the time is who it could always operate with. But with this new capability that we have in hardware that's capable in space, we can now change the software and make it do things we hadn't intended. So the SCAN testbed has 3 of these new types of radios, and one of them operates at a much higher frequency than current radios. And a higher frequency means that you can send a lot more data through. So if you're doing a science mission and you're looking at rocks, you can send a lot more information about the geology back versus the radios that exist now, where you might be limited to how much you can send back in a period of time. And the frequency the spectrum right now is also very crowded. We have to share when we can send the information. And with the new frequency, we can not have to share the spectrum as much. We can operate whenever we want. So that's what the SCAN testbed's all about, is these new radios that can be configured, can be changed after we launch. And we operate them, but we also, the neat thing about this now that we have new software, are the ability to put new software in space. We can also modify the software and look into new things that we hadn't thought of as far as networking. So NASA typically is like the old phone system where you would make a phone call and then talk and then hang up.
Okay.
Call that number directly. So, you know, when we use networking on our computers, we send information and we don't care how it gets there. We just know it'll get there. Networking for NASA's 10 years behind in space. And so new ideas on how to route information through the space is one of the things that are being studied with the SCAN testbed.
Very interesting. It sounds like there's a lot of different possibilities. How do you go about demonstrating this technology at this point?
Well, right now we have what we call experimenters, people who we've requested through the NSPIRES program to write new software with a lot of new ideas. Using like industry can propose experiments. NASA, we have a lot of NASA experiments. Universities, they have ideas on new ways of doing networking, new ways of doing navigation that they can propose to us, and then they can write the software, they develop the software in their system or our system. They have to test it here. We have a duplicate of the test bed here at NASA Glenn, and they have to test it here. We want to make sure it works. And then we can upload that software and into space and try it out. And then the really nice thing is that this test bed is on space station, so it operates in a similar way as a mission might operate. It's in a low Earth orbit. It gets radiation. We have a lot of different networks it can interoperate with. And so that helps us to have that test bed on space station be able to look a lot like a mission might look in the future. So when we're testing new concepts, we can feel confidence that a mission might want to use it. And the problem we always have is we develop new technology, but missions are afraid to use that technology, kind of the way if you go to buy a car, you don't want to be the first model year to buy that. You don't want to buy the first model year of that car because there might be bugs in it.
Sure.
So missions kind of use what already exists because they're afraid to be the first one to try it. And so with this test bed, it gives us the opportunity to try things that missions then can go use the second time. So it's been an ideal test bed for that.
So you can demonstrate that it does in fact work in space and it's safe to use on other missions.
Absolutely. And so we've been doing a lot of papers, but having the experimenters actually do it themselves is even better. To be able to try it out yourself is ideal.
Absolutely. Are there any ideas or experiments that people have come up with that you're really excited about?
There's a lot of them. Let me start with how we're actually using it in the next few weeks, and that'll give you an idea.
Great.
Actually, something we're doing here at Glenn, one of the radios was built by General Dynamics, and it's actually a fifth generation. General Dynamics is who we went to for a lot of our radios, but they were all hardware radios. And so with General Dynamics, we wrote new software because the initial software that was written worked almost perfect, but there was a few little bugs, things that didn't work quite as expected. And in the old days when you have hardware, you would have to live with those or delay your launch and build new hardware. And so we added new software to be able to modify it and have it work now. And so that's been exciting. We're doing that right now. And that can be done in a 3-month time. You could say, oh, there's something wrong with this, modify it, test it on the ground, and upload it if it's a minor modification.
Sure, as opposed to if you had it in space and then had to launch a new one into space with new hardware, which would take possibly years, right?
Right. And what's really neat is we have not just NASA users, but like non-NASA users. The Air Force is looking. They have a new campaign they call CNAV. U.S. Air Force Space Command is testing their modernized civil navigation message capabilities of their new GPS satellites. So they've asked us to receive their signal and send the received signal to them, and they can analyze and see if their message format looks as they expected. So I've been working with the Air Force on that, and they think we're an ideal platform for that also. So one of the areas we're focused on is communication, navigation, and networking. So in navigation, the ability to determine the position and where you're going is ideal, and being able to there's new technology that can make that better and better. And the Air Force, who runs the GPS system, they've been working with us to improve their new satellites and understand their new satellites.
Well, it sounds like this has a lot of potential.
It really does.
And y'all are getting ready to go into a pretty active phase of the experiment, is that right?
We really are. We have over 30 active experimenters. We've received over 40 proposals, and we have right now probably 30 experimenters we're working with actively. And so we're pretty busy. Some experimenters are 48 hours. They want to run and collect data. Some of them are a few hours a week to see how things change over time. So we have probably 30 different organizations, including international organizations that we're working with to study how networking, delayed tolerant networking, which, when you're in space, you don't always see who you're talking to. So you need the ability to be able to deal with disruptions, and then, of course, the delay of space. And so there's new technology called delay tolerant networking or disruptive tolerant networking that even the international community is looking at, and we want to make sure that how we implement that and how the international community implements it operates together. We both follow the same standard, but we might implement it differently. We want to make sure they interoperate. So we're working with international communities on that.
Well, that's great. Thank you so much for telling us all about it. We wish you good luck with that, and we hope to hear more about it in the future.
Okay, we'd be happy to talk more about it to you.
All right. We'll check back after you have some more results to share with us. Thanks so much.
Thank you.
That again was Sandy Johnson, who is the Deputy Principal Investigator for the SCAN experiment. And SCAN stands as an acronym for Space Communications and Navigation Testbed, a technology demonstration experiment that is currently on the space station's truss and has been operating for about a year now. We've talked a few times over the course of the week about how flight engineers Karen Nyberg and Luca Parmitano have been participating in an ongoing investigation to learn more about fatigue on long-duration missions. It's called the Reaction Self-Test, and they did runs of that first thing when they woke up this morning, and will do it again before they go to sleep for the night. It's a portable 5-minute reaction time task that monitors the daily effects of fatigue on performance while on board the space station. What investigators hope to learn could prove valuable not only to astronauts, but also for folks here on Earth who work high-stress, long-hour jobs. And the Marshall Space Flight Center's Lori Meggs talked with the principal investigator of that experiment to learn more about the study and results so far.
It includes two elements. One is a set of quick self-reports on the support computers on the station, where it asks you when you get up, when you go to bed, how long do you sleep, what was the quality of your sleep. It also asks about your workload, your tiredness, your fatigue and exhaustion. So there's a host of things it asks very quickly, and you enter those things, and then it goes on to the second element, which is a performance test. It's a 3-minute long, sustained attention-demanding task, but it's very simple. It's just reaction time. You have to watch the screen of the computer, and as soon as the signal comes on, hit the button as fast as you can. We measure that in thousandths of a second, and you never know when it's going to come on again. So it locks on the frontal lobes of the brain and the attention circuits, and you got to try to hold those stable. The reason we study those is because they are particularly, those circuits and that response, it is particularly early warning sign of the effects of fatigue and tiredness on the brain.
So what have we learned so far?
Well, number one, we've learned that astronauts are terrifically good research subjects. They're so conscientious, even despite the fact that they're working very hard up there on operations issues. They did the experiment. We have quite a lot of data down already. We're not quite done, so we're not ready to give everything away at this point in terms of what we're learning. But already we know that they can hold, most of them can hold their performance very high, even on this quick, demanding task, through sheer will in the face of high workload and some sleep loss. But we also know there's a limit to that. So their tiredness ratings indicate that the more tiredness they're reporting, the poorer that performance is. So there's definitely the potential for degradation of that performance from just being overly tired. We'd love to know what's causing the tiredness. Is it sleep? Sleep quality, sleep duration? Is it workload, the intensity or meaningfulness of the work? Is it simply the environment of spaceflight, microgravity and other things? And we're not going to have the full answer to that, but we're going to have a pretty good idea of where some of the major challenges are to the astronauts to maintain effective performance capability.
How many subjects have you tested so far, and how many are left?
We have 23 enrolled in the protocol. We have 24 as our target, so we're very close by way of enrollment. But in terms of where they're at in it, we've got 19 who've completed all their data, and then another 5 more. We're in various, or 4 more various stages and 1 more to enroll. But we're talking about nearly 1,500 downloads from station, because we're tracking them throughout the entire mission. And we particularly want to know whether there are changes in these functional measures and self-reports when they get sleep shifted, when they do an EVA and have a long day, or when other things occur that are challenging to them, and workload is the separate chronic effect that we're looking at across the mission.
So what are the space and Earth applications for your research?
Well, we're lucky. In this area, they're widespread. The ability to maintain human capability in extreme environments or monotonous conditions or high workload or partial sleep loss is relevant to a wide number of things that the military does, security guards at power plants and operators, all the transportation modalities, long-haul pilots, the truckers, to maritime. And so there's a large number of tasks in which you want people to be attentive, focused, react correctly and quickly, but do it with inadequate sleep or at night or with high workload or other stressors. So it's got very good generalizability, and in part, the utility of this will probably spread rapidly in the civilian sector once we're able to show how useful it is on spaceflight.
That again was an interview that Marshall Space Flight Center's Lori Meggs conducted with the principal investigator of the Reaction Self-Test experiment, David Dings. That, and again, is an experiment that both Luca Parmitano and Karen Nyberg have been participating in all week long and are doing so again today. They did a test one of the tests that he talked about this morning as soon as they woke up, and we'll do another one right before they go to bed for the night. This is a more recorded video of Flight Engineer Karen Nyberg working earlier today to get the InSpace 3 experiment set up inside the space station's microgravity science glove box. That glove box is used for a number of different experiments on board the space station, and the astronauts often make use of it for setting up different types of experiments. And to tell you a little bit more about the glove box and how it works, we have a feature that we're going to play for you here next on NASA TV. This is Mission Control Houston.
The Microgravity Science Glove Box, located in the Destiny Laboratory, provides 9 cubic feet of enclosed workspace for conducting a wide variety of experiments that require liquids, combustion, or hazardous materials. ISS crew members can safely use its rugged gloves to work in a sealed environment without the risk of releasing any small parts, particles, fluids, or gases into the rest of the laboratory. The Structure and Liftoff in Combustion Experiment, or SLICE, utilizes the MSG to study and work with fire in microgravity. SLICE allows astronauts to photograph and measure the shape and temperature of flames produced by various fuels and sizes of burner nozzles. These assorted flame shapes and sizes are then modeled to help scientists develop more efficient engines and furnaces here on Earth. The MSG is also used to conduct the BASS experiment, which stands for Burning and Suppression of Solids. Instead of measuring flames from burner nozzles, the BASS experiment observes and models the geometry of flames on solid spheres and flat surfaces. These controlled fires are then extinguished in a variety of ways to look for the best strategy to use for suppressing flames in microgravity. Improved fire detection and suppression systems for use on Earth and the ISS can then be designed from this information. The MSG is also used to accommodate tests for heating liquids in the Boiling Experiment Facility, a small container that includes 2 types of heating arrays, high-speed video cameras, and a variety of tools for measurement. Experiments in the BXF try to determine critical heat flux, the point at which a heat source becomes so hot that the liquid can't actually touch it. Interestingly, the information from the study of critical heat flux is used to design enhanced cooling systems. The BXF's heating arrays are also used to study the shape and buoyancy of bubbles. The high-speed cameras in the BXF capture the growth, detachment, and motion of two types of vapor bubbles: small individual bubbles and larger bubbles that have merged together. Without the microgravity science glove box aboard the ISS, there wouldn't be a safe way to work with dangerous materials and conditions to carry out these compelling experiments.
That again was a closer look at the microgravity science glove box, which Karen Nyberg has been using today as she set up the InSpace 3 experiment for some runs that are coming up for that. One other experiment that she and Luca Parmitano have been taking part in lately and continue today is the PRO-K study that investigates how what astronauts eat can predict and protect against the changes in their bone metabolism while they're in space and once they get back to Earth. NASA studies the effect of spaceflight on bones in several different experiments, but this is actually the first that looks at whether diet can be used as a countermeasure. The experiment's proposal is that a decrease in the animal protein to potassium ratio in an astronaut's diet will lead to less loss of bone mineral. And during their stay at the station, the crew members who are participating in the experiment go through 5 dietary intake sessions, 5 blood collections, and 5 24-hour urine collections. During the intake sessions, the crew member would eat either a high or low ratio of animal protein to potassium for 5 days straight, while taking urine samples each morning when they wake up, and then on the 4th and 5th day they take an additional urine sample, or additional urine samples throughout the day, and on the 5th day they also take a blood sample. Samples are then returned to Earth for study, and in all 16 crew members are going to participate in the study, which started back during Expedition 21. If it works, this will be a very good countermeasure for astronauts because it doesn't require any extra effort for the crew, just an adjustment to their diet. For today's part of the experiment, Parmitano is wrapping up his run of it and will be finishing his intake session and doing the extra urine collections and a blood sample collection, while Nyberg is just beginning hers. Seeing live views here from the exterior of the International Space Station with a good look at the top of the screen, at the space station's robotic arm, which we saw Nyberg and Cassidy training with from inside the station here at the space station's robotic workstation inside the Destiny laboratory. That's one of the main tasks on their agenda for today, but another one for Cassidy is some work inside the JAXA Kibo laboratory on the multi-purpose small payload rack. He's doing a checkout today of the chamber, the combustion chamber of that rack. The multi-purpose small payload rack has 2 workspaces and a work table, and they can be used equally as a laboratory on the ground, putting equipment or making equipment free and easy to access, or for general interfaces with power supply, communication, and videos. some video recorded earlier today of Cassidy working inside Kibo at that rack. You can get a look at what it looks like. Again, it's the multi-purpose small payload rack, so it's a little smaller than some of the racks we see the crew working with, which tend to be about refrigerator size, such as the one that Cassidy did work on yesterday, the Express Rack 7. This rack can be used for a number of different space environment experiments, including science and educational missions as well. It includes a workbench for maintaining equipment and exchanging samples, as well as reviewing data from the experiments. Also a small experiment area for science experiments that don't need many resources, such as crystallization experiments. That particular area has vibration isolation from the rest of the space station to make sure that the different vibrations on the space station don't interrupt the experiments that need steady and stable environment. And it has the combustion chamber, which is what Cassidy is working on today. That's a double enclosed chamber for combustion experiments that look at fire and how to put it out on the International Space Station. Everything that would be necessary for such experiments is integrated into the combustion chamber for this multi-purpose small payload rack.
Unix station count 2 for Biolab.
Go ahead, Luke, count 2.
Hey Bernd, whenever you guys are ready, I'm free to start working again in Biolab.
Stand by, Lucas.
And as you just heard, Luca Parmitano call down. He's ready to get back to work on the biolab work that he's been doing today, similar to what Cassidy is doing here. He is doing some maintenance on the biological experiment laboratory. In particular, he's troubleshooting the handling mechanism drawer for that experiment, or that laboratory, which is located inside the Columbus module. It's a European Space Agency laboratory that is a multi-user research facility used to perform space biology experiments on microorganisms, cells, tissue cultures, and small plants, as well as small invertebrates.
In the meantime, can you gather the PPE already, and we will come back to you once we have it. And the vacuum cleaner as well.
Okay, I have the PPE with... Copy, I have the PPE with me, and I'll just wait for you. I'm ready whenever you guys are.
Okay, we copy that, Luca, and this is Lionel on the loop.
Oh, sorry, Leo. I didn't recognize your voice. It's good to talk to you.
Again, that was Parmitano talking with the flight controllers in the European Space Agency's Control Center about the work he's getting ready to do on the Biolab laboratory. That's a biological experiment laboratory. And as I was saying, it is aimed at helping scientists gain a better understanding of the effects of microgravity and space radiation on biological organisms. That facility includes an incubator, a microscope, a spectrophotometer, which is an instrument used to measure the spectrum of light absorbed by a sample, and also 2 centrifuges that can produce artificial gravity. All of that is integrated into a single space station payload rack. Again, it's located inside the Columbus laboratory. And it was delivered to the space station on STS-122. The handling mechanism that Parmitano is working with today is a robotic arm that provides an interface between the experiment containers that hold the samples and Biolab's analytical instruments, such as the microscope and the spectrophotometer.
Space to ground 4. Okay, thanks. We'll take that one back, and we'll be getting set up for Chris's PMC. Karen, while I have you, I wanted to talk to you about the cabin temperature in the lab. We are showing some problems with node 3 condensate collection. We're seeing a wet sensor in the CCAA, and one way to help fix that is by lowering the temperature in the lab by 1 degree Celsius. That would bring you down to about 72 degrees Fahrenheit. So we just wanted to check with you guys that that would be okay with you. It would probably be for overnight. We just wanted to check your comfort level on that.
We'll just get out our sweaters. No problem.
Okay.
Yeah, just do what you have to do.
Great. Thanks, Karen. We appreciate that. And we're planning on SSC-15 for Chris. Is that correct?
Yeah, that works fine. Thanks.
Thanks, guys.
Capcom Megan MacArthur there talking with the crew on board the station about a plan team here on the ground has to lower the temperature inside the laboratory, the Destiny laboratory, in just a bit to help with some condensate issues they noticed in there. One other experiment that the Expedition 36 crew members have the option of taking part in today is the Crew Earth Observation Program. As they have time, astronauts on the station can take advantage of special opportunities to photograph specific features on the Earth as they fly over, and then those photographs record the Earth's surface changes over time, as well as dynamic events such as storms, floods, fires, and volcanic eruptions. Those images provide researchers here on Earth with good data for better understanding the planet, and the space station has provided more than 1 million photos over its lifetime, with Expedition 36 submitting several thousand on their own. Today, the crew had several opportunities to participate in that program, starting with another opportunity to photograph polar mesospheric clouds. They were given a couple of opportunities to capture some photos of these as well, but they are difficult to detect. They're high altitude, wispy, bluish clouds that are just visible above the stratosphere after sunset at the surface while they're still illuminated by the sun. We're currently in the Northern Hemisphere's season for observing such clouds, and they have the crew has actually 4 opportunities today to take photos of this phenomenon over North America. Photospheric clouds have increased in brightness over the last 4 decades and are appearing further south and have even been observed from Colorado and Virginia, which may be related to climate change. So several of the opportunities that the crew has to take part in the Crew Earth observation are related to that today, but a number of other photos that have been taken over the course of the station's history can be seen online at the Crew Earth observation website, which is eol.jsc.nasa.gov. Again, you can see it here on the bottom of your screen, eol.jsc.nasa.gov. we're coming up now on the end of today's Space Station Live. Coming up next on NASA TV, you'll get a look at some of the other activities going on at NASA centers around the country in the NASA TV video file. That's going to begin at the top of the hour, 11 a.m. Central Time here on NASA TV, and that's coming up next. Then we'll be back tomorrow at regular time, 10 a.m. Central, with Space Station Live. And you'll want to stay tuned after that at 11:40 a.m. Central Time for a chance to hear the flight engineers Chris Cassidy and Karen Nyberg talking with Minnesota Public Radio and the U.S. Navy. That's going to be coming up again at 11:40 a.m. Central Time tomorrow, following our regular 10 a.m. Central Space Station Live. All that's coming up here on NASA TV, and this is Mission Control Houston.